All right, new week, new problem. Day 66. All right, it's the LeetCode medium, and it's a house robber 3, and it's under the backtracking pattern that we've been evaluating the last, what, 3 videos? 3 videos. And here's the problem statement. So a thief has discovered a new neighborhood to target, where the houses can be represented as nodes in a binary tree. The money in the house is the data of the respective node. The thief can enter the neighborhood from a house represented as root of the binary tree. Each house has only one parent house. The thief knows that if he robs 2 houses that are directly connected, the police will be notified. The thief wants to know the maximum amount of money he can steal from the houses without getting caught by the police. Okay? The thief needs your help determining the maximum amount of money he can rob without alerting the police. So it's worth noting that if he robs 2 houses that are directly connected, the police will be notified. Okay, and he wants to know the maximum amount of money he can steal from the houses without getting caught by the police. So without the police being notified. Let's look at this diagram. Should explain it. So this is a binary tree, and it's represented in an array here. So this level order traversal of a binary tree. Nodes in yellow. Node in yellow is the root. Blue is the second level. Green is the third level. So this is the parent of these 2, and these 2 are the parents of these 4, as you can see here in this diagram. And now they represent their neighborhood relationships, yada yada yay. The value is the amount of money he can rob from each house. So if he picks the first house, he can't pick these 2 because they are right next to this one that he just picked, the 3 that he just picked. And however, he can pick these grandkids, right? He can't pick these parents. He can pick the grandparents. He can't pick the parents, but he can pick the grandkids. So you can't pick anything that is side by side. Well, if you pick one, you've excluded the one right beside it. And if we go this route, we see that, oh, he can make 29 units of valuables, money, whatever, if he goes this route. Now, if he skips that, he can pick what's in the middle, but he cannot pick what's at the end, as you can see, as shown in red. And what that does, basically, as you can see, what that sums up to is 30. So you can get 30 this way. Now, this is another way he could do things, and he would get 47, which is bigger than 30, right? So he skips the first one, he picks this one, but then he skips this one and picks the grandchildren, and he still fulfills the rule where, oh, he didn't pick any side that shared an edge, basically. Once he picks one side, he skips before he picks another one. He skips a level before he picks another one, and he gets 47. And so hopefully we understand the problem so far. Let's look at the solution. So in the naive approach, I mean, we're gonna end up checking every single possibility, and that gives us 2 to the power n possible ways to rob the neighborhood, which is not what we want. And so we're not going to calculate every single possibility. We're going to use backtracking in a sense. Although it's giving me greedy algorithm vibes, but let's see what we have here. So it's a lot of text, but I'll run through it very, very briefly so we can get to a diagram that will make things clearer. So, so we're recursively exploring all possible combinations of backtracking whenever we encounter an invalid combination, which is the story of backtracking. And we can avoid evaluating redundant solutions and reach the optimal combination more effectively. So we have these functions. A rob function takes the root node of the binary tree as the input and calls the heist function that returns the maximum amount of money that the thief can rob from the binary tree. And I already have the code set up. So we have a rob function that takes the root node of the binary tree as input, and a heist function that returns the maximum amount of money that a thief can rob from the binary tree. And I define those here, a rob and heist. And if you can preview the code right now and see that it's not too bad, right? Not a whole lot of steps. Still it's medium because, I mean, it's recursion, right? The function is going to call itself. So that just boosts the complexity significantly. So the heist function recursively calculates the maximum amount of money that can be robbed from a subtree rooted at a node. Okay, it returns a pair containing the values of include root and exclude root. Worth noting, include root, exclude root. Include root contains the maximum amount of money that can be robbed from the subtree rooted at the node with the root node included. So that we included the root node. And as you can imagine, exclude roots, we excluded the root node, as you can see here. And function proceeds through the following steps. So this is what heist, right? This heist function does at any given root. We call it for the first root, but it's going to call itself. And okay, if the tree is empty, right, return 0, 0, which means the include roots represent include and exclude respectively. So if it's empty, if the root is null, there's nothing there, just return 0, 0. Otherwise, it recursively calculates the maximum amount of money that can be robbed from the left and right subtrees of the root node, which is what we're going to see here. It's going to call itself, basically. So the left subtree here and the right subtree here. Then it stores the maximum amount of money that can be robbed from the root node in the include root, right? That's the first thing, the one on the left, right? Left is include root, right is exclude root. And it computes the maximum amount by adding the value of the root node to the following. So the maximum amount of that can be robbed from the left subtree, excluding the respective parent node, and the maximum amount that can be robbed from the right subtree, excluding their respective parent node. So left subtree, right subtree, and it includes the root how. It says the root data, whatever we pass in as root, dot data plus the left subtree, index at 1, because again, we're excluding root, including root on the right, and we're excluding root on the left, as you can see down here. 0, 0. All right. Alternatively, it completes the maximum sum of money that can be robbed from both the left subtree and right subtree of the root node, excluding the root node itself, and stores it in exclude root. Finally, the heist function returns a pair containing the values of include and exclude root. Okay. The rob function returns the maximum value from the pair obtained by the heist function, which is the maximum amount of money the thief can rob from the houses in the binary tree without alerting the police. I think this diagram can help make things a bit clearer. Or I think this diagram explains things a bit better than just looking at the code. So we have this tree, and when we call this algorithm heist recursively, it is gonna keep going. So far the root is not null until it gets to the base case, which is gonna bring us to evaluating this node, right? This last node here, right? Because it's valid, but it doesn't have any left or right. And basically, what we're gonna do is evaluate including the root first of all. And that's gonna give us root data itself, and it has no children. So the left and right subtree are going to be 0. Basically going to be 0, 0, because it's going to call heist again, and it's going to be 0, 0. So including the data is going to be itself, and excluding it is going to be 0. And that's what we're going to have, excluding the subtree. So the max of the left and right subtree is going to be 0. That's why this is going to have 0 initially. That's what happens when we call this function first. And then it's going to do that for every single leaf node, basically, and it's going to give a similar response for every single leaf node. Now, when things change is when the recursive stack is going back to the top, right? It's being popped and going back to the next level of things. So now things are going to be a bit different, because now there is a left and right. There's a left and there's a right, right? Left and right subtree. So it's going to calculate the left and right subtree. And what's that going to do? Basically, including the root is gonna add itself, right, plus the left and right subtree. So we can see that the left and right subtree index at 1, this index at 0, index at 1 is 0 for these two. So that's why that root data plus 0 is going to be 8, and that lets us because we realize that we can't include these values if we are picking this one. So this represents if we pick this one, and then this 23 here represents if we don't pick this one, in which case we are going to pick the maximum of whatever of the values here, which is in this case is 12 and 11 and adds up to 23. So that's what makes right? The exclude root, right? Have anything to say here in this case. And so we do that for this as well, right? We have one. If we include one, then we cannot include these two. Remember that from the explanation. And if we have 6, which is when we include these two, then we cannot include 1. And that's why it looks like that way. This is what that looks like for code. Now, I admit it doesn't translate neatly, but stepping through this with a debugger could help, right? With some generous console.logs, which you will find down here, right, in the link into the code in the description that you can run locally. I put a bunch of console logs everywhere to see what exactly is going on. And basically that's why this is a medium problem, right? Because it's not super intuitive. Yeah. And then lastly, we check this node, the 5, which is the root node. And if we include it, it's going to have a certain look, right? 34, that's the best we can do. And if we exclude it, we're going to have 29 at best. And so we're going to include this node in this case. Yeah, and that's what we have so far. And then we can have another example, right? Where picking one or the other gave us a different outcome, basically. Where we got in this case 40 instead of 34 by picking specific nodes at each level instead of just picking the whole level itself. And so yeah, it's quite ingenious how it all works, especially how the code pans out, right? The recursive calls that cascade and end up starting from the ground floor before heading back to the top. The video has gone on for a while, so remember, code is in the description. You can check it out. And it's a summary. Time complexity though is O of n, because that's the number of nodes in the tree since we visit all nodes once, right? We have to check every single possibility. And the space complexity is O of n, since the maximum depth of the recursive call tree is the height of the tree, which is n in the worst case. So it's a linear list, worst case, right? And each call stores its data on the stack. And that's all for this problem. See you in the next one. Ciao.